In 1957, the sky isn't just pretty to look at. It's a window to the insanely powerful universe we live in. There's so much happening out there that we on Earth are usually oblivious to what's really going on. Why are we here? Why do we have stars and galaxies? It could have been something else entirely. Even if these cosmic events eventually affect us, we tend not to pay attention until things become serious, and that might have happened again. Throughout history, Betelgeuse has been one of the brightest stars in the sky, but now it's begun vibrating violently, and something terrifying is happening. Join us as we bring you all the details about what's happening with Betelgeuse and how it might change our future along with its own. Betelgeuse isn't an ordinary star. It never has been. It's one of the largest stars ever discovered, so massive that it makes our sun look small in comparison. With a mass roughly 20 times that of our sun, Betelgeuse bears the unmistakable mark of a supergiant star. From our vantage point, it might appear as just another distant star, but in reality, it holds a far more profound status. Located more than 640 light-years away from Earth, this distance might seem inconsequential at first glance, but in cosmic terms, it's monumental. If we could travel at the speed of light, an option currently beyond reach, it would still take over 640 years to bridge the gap to Betelgeuse. Under normal circumstances, we would need over 12 million years, longer than human civilization itself, to make the journey. This perspective highlights the immense power of this single star, which has now begun vibrating violently. We often think of stars as calm, serene objects simply existing in space, regardless of their size. But Betelgeuse proves that assumption wrong. The recent vibrations have scientists baffled. Betelgeuse hasn't been still. It's always been known as a pulsating red supergiant that changes over time. When the star expands, it looks brighter, and when it contracts, it appears slightly dimmer. These fluctuations in luminosity take place over extended periods, from tens to hundreds of days. Betelgeuse's brightness varies widely from around plus 0.5 to a more intense magnitude of 0, a considerable difference for a star. These changes in brightness follow recurring patterns, with the shortest cycle lasting about 185 days and the longest extending to around 2,335 days. Sometimes these fluctuations are more periodic, following a recognizable pattern. This phenomenon is called the V-band magnitude. In February 2021, it registered one of its lowest V-band magnitudes at plus 1.614. While still bright, this marked a departure from Betelgeuse's usual radiance. Betelgeuse's significance is not just defined by its luminosity variations. Its distinct reddish hue is due to its cooler surface temperature, about 3,500 Kelvin, much cooler than our Sun's 5,500 Kelvin. While our Sun is smaller, it's still brighter due to its higher temperature, emitting more energy per surface unit. Betelgeuse's cooler temperature leads to a reduced energy output, making it appear dimmer despite its size. Although generally stable, the recent shift from calm to chaotic behavior has intrigued scientists. A popular theory is that Betelgeuse's helium shell is undergoing fusion. As Betelgeuse progresses through its life cycle, it depletes the hydrogen in its core, fusing it into helium, a typical behavior for red supergiants. When hydrogen fusion slows, the star's outer layers expand, entering the red giant phase. Helium accumulates in a shell around the core, where intense heat initiates secondary fusion, forming elements like carbon and oxygen. The periodic buildup and release of energy during helium shell burning create instabilities, causing expansion and contraction and affecting the star's brightness. Helium shell burning, however, is less stable than hydrogen fusion, leading to energy fluctuations that impact the star's structure, causing the rhythmic pulsations we observe as changes in luminosity. These strong stellar winds can carry away significant mass from Betelgeuse's outer layers, redistributing matter and influencing its evolution. This mass loss leads to rhythmic pulsations, almost like a heartbeat, where we see changes in luminosity. While this process is plausible, confirming it requires extensive analysis. Scientists use methods like photometry and spectroscopy to monitor stars like Betelgeuse. Photometry tracks luminosity changes over time, revealing dynamic behavior, while spectroscopy examines emitted light across wavelengths, offering insights into temperature, composition, and motion. The synergy between these techniques allows astronomers to connect Betelgeuse's internal processes to its luminosity changes, painting a holistic picture. Astrophysicists employ computational models to simulate Betelgeuse's internal dynamics, bridging theory, and observation. These models consider stellar structure equations and nuclear reactions within the core, helping scientists study Betelgeuse's pulsations in virtual scenarios. But there's more to the story. Within stars like Betelgeuse, stellar convection may also play a role. Convection transports energy from the core to the surface through buoyant cycles of hot and cool material, radiating energy as light and affecting the star's brightness. These convection currents can drive pulsations as energy transport fluctuates between periods of increase and decrease. In binary star systems, material transfer can trigger pulsations. When two stars orbit each other closely, gravitational forces allow mass transfer from one star to another, altering internal pressures and fusion processes and potentially disrupting equilibrium. These changes can induce rhythmic expansions and contractions in luminosity, marking the star's attempt to stabilize amidst these forces. Mass exchange can also alter the evolutionary paths of stars in binary systems, redirecting them in ways that wouldn't occur in isolation. Historically, stars were studied as individual celestial entities, but now we know interactions like these influence stellar behavior. Advanced telescopes and research allow us to uncover these interactions and learn the truth about what's happening in our universe. The universe is filled with marvels, and one of the most intriguing stars is Betelgeuse. This star has been pulsating, catching the attention of astronomers, and there's one explanation we've avoided acknowledging. Betelgeuse might be ready to go supernova. In its late life stage, like other massive stars, Betelgeuse balances gravity and nuclear fusion in its core. Gravity, the force pulling matter inward, and nuclear fusion, which generates outward pressure, hold the star together. But as Betelgeuse exhausts its nuclear fuel, this balance shifts, causing the star's core to contract as gravity prevails. This contraction increases the core's temperature, sparking a new, more intense fusion phase where heavier elements like helium and carbon are formed. This process eventually leads to an iron core, which is unique because iron fusion absorbs rather than releases energy. This disrupts the core's energy output, leading to collapse and an eventual supernova explosion. If this happens, the outer layers of Betelgeuse would be ejected at incredible speeds, generating an intense burst of light visible across the sky. The shockwave from this collapse could tear apart the star, rivaling the brightness of an entire galaxy. If Betelgeuse were closer to Earth, we'd face catastrophic effects, with gamma-ray bursts, GRBs, posing extreme risks. GRBs could deplete our ozone layer, exposing us to harmful UV radiation that could impact human health, agriculture, and ecosystems. The electromagnetic pulses, EMPs, from the supernova could disrupt electronics, causing power outages and impacting critical infrastructure. Beyond these immediate effects, the energy released could alter Earth's weather patterns, causing temperature shifts that might impact global ecosystems, agriculture, and even food security. A nearby supernova could also accelerate cosmic rays, posing hazards to astronauts, damaging satellites, and affecting astronomical observations. Betelgeuse's fate could be more than a supernova. If it collapses into a black hole, its gravity would exert extreme tidal forces, potentially disrupting nearby planets and celestial bodies. Matter around Betelgeuse could be drawn into an accretion disk, emitting radiation that could harm atmospheres and ecosystems. The black hole's gravitational pull might perturb orbits in our solar system, potentially destabilizing it. Although Betelgeuse's distance from Earth makes it unlikely to directly impact us, this star's eventual supernova or transformation into a black hole promises either a stunning light show or a far-off cosmic event. Would it be a supernova spectacle or a silent transformation into a black hole? Let us know your thoughts. If you enjoyed this deep dive, give us a thumbs up, and we'll see you next time.